Well, hey, welcome back to Calculus 1. We are making really good progress on this integration thing. And I want to work with you on the next stage of our journey into the world of integration, which is going to be on the indefinite integral. This follows right on the heels of the definite integral. And then in our next section, looking forward, we're going to connect the two with the fundamental theorem of calculus, one of my favorite theorems in the whole wide world. Just a gorgeous theorem. So I have 4 objectives for you for section 5.3 in our textbook. The main thing, I don't know if any of these are the main things. I want you to understand what an antiderivative is and how to tell if a function is an antiderivative. I want you to know the difference between the general antiderivative and what a particular antiderivative is. I want you to learn the power rule for integrals and some other simple antidifferentiation rules, all of which are the complements for the respective differentiation rules. And we are going to work on some basic differential equations with initial and boundary value problems. So I do have a number of relevant Lightboard videos on YouTube. In case you find those helpful, I have those 5 up there, among some other ones. They all kind of fit together to tell the complete story. So where are we at in the story so far? So far we've learned in section 5.1 how to approximate the area under a curve. And in section 5.2, we learned that the definite integral is defined as the limit of an approximation. That is to say that the integral from a to b of f of x dx is equal to the limit as the width of the partition goes to 0 of the Riemann sum of f with partition p and sample point set c. And then we made that specific with some sums, with the right sum, with the left sum, etc. We also learned that the definite integral is the exact net area under the curve, and that stuff above the x-axis is plus and stuff that below is minus. And we learned that some definite integrals can be computed by Euclidean geometry, but we didn't step toward doing more or less arbitrary integrals. We just kind of said, okay, we can do some by geometry, we can do some by approximation, some we can do by doing this formal limit process. I didn't give any examples of that, but there are plenty in the book. And so our next step is to learn about indefinite integration, and then coming up in section 5.4 is the connection. And what connection between the definite integral and the indefinite. And that's what the fundamental theorem of calculus. Part 1. There are 2 parts to it. Yeah. Okay. So let's start looking at what the indefinite integral is. This discussion is going to start with a pretty blatant typo. Oh, that is just terrible. I put stuff inside of the frac. That's okay. Okay, so it was going to be sloppy because I left out the A-B stuff. Now it's just sloppy because I can't tack correctly. I'll fix this in the notes that I get posted. Sorry. Okay, so I need to define for you what an antiderivative is. So what we're going to do is we're going to take our function little f, and we're going to find an antiderivative for it, capital F, and it's defined by the act of differentiation. So an antiderivative is a function capital F that I can differentiate, and I get back my little f. This is supposed to say f prime equals d capital F dx equals lowercase f. That's what that's supposed to say. Sorry. I'll go ahead and write that here. I gave it a look over. I don't know how I missed that. Okay, the more precise definition for antiderivative allows us to say it's an antiderivative for f on a, b. It's just a function, capital F, such that f prime is equal to the derivative. F prime is equal to f. So if I differentiate the antiderivative, I get back the thing I started with, and then on this domain restriction right here. And this definition is useful for things like piecewise defined functions. This lets me define piecewise defined antiderivatives. For what that's worth. So if you're not dealing with piecewise defined functions, then this one up here is sufficient. That is to say that we find antiderivatives by doing differentiation in reverse. We're just going to anti-differentiate, opposite of, anti-differentiate. So let's play with a couple of functions. Let's find 3 antiderivatives for x squared. Okay, so now I have to ask myself, if I let that be lowercase f, what function do I differentiate to get f, question mark, all right? For what capital F is d capital F dx equals x squared. Let's see here. So I remember that this is a polynomial. Polynomials use the power rule, which means that it's going to be something like the power rule. And I remember that when I took d dx of x to the n, I got n x to the n minus 1. So when I differentiated, I subtracted by 1. So let's try increasing it by 1. So let's try f equals x cubed. And if I differentiate that, then I'm going to get capital F prime. I need that to be equal to lowercase f. And if I do that, I get an x cubed minus 1. So that's just x squared. But then I have a 3 out front. And I can't have that 3 because I don't have a 3 right there. So I need to divide by 3 in order to get it correct, so that they'll cancel right here. And now I just have x squared as desired. Ooh, I know another way to do another one. What if I let capital F equals x cubed over 3 plus 1? Because then when I check whether it's an antiderivative by taking the derivative of my antiderivative, my proposed antiderivative, I'm going to get 3 times x cubed over 3 plus 0, which is just equal to, sorry, that's a square, which is just equal to x squared. Okay, there was nothing special about that one, so let's try another one. Let's try letting capital F equals x cubed over 3 plus pi. Then lowercase f, which had better be equal to capital F prime, is going to be x cubed over x squared over 3. Taking a break with my mind. 3 times x squared over 3. There we go. I did the power rule plus 0. Okay. So in these cases, I've got a plus 0, plus 1, plus pi. There's nothing special about that constant. Let's do it for cosine. What function do I take the derivative of to get cosine? Hopefully me writing that down was enough time for you to think back to the work that we did in chapter 3. I take the derivative of sine to get cosine, which means that if lowercase f is equal to cosine of x, then capital F is equal to sine of x. And I could say sine of x. I could say sine of x plus 2. I could say sine of x plus pi. Or, I mean, why not just write it in general? f4 is equal to sine of x plus, let's just add some constant to it and call that constant c. Because when I take the derivative of a constant, I get 0, which is what I need. Okay, so these two examples where I have a whole family of antiderivatives parameterized by the constant of integration give rise to the general antiderivative. The general antiderivative is stated as this. If capital F is any antiderivative of a lowercase f, then capital F of x plus c is the general antiderivative. So when we want to write the general antiderivative, we're going to antidifferentiate, and we'll add some generic arbitrary constant c, and then sometimes we need to find out what that value c is. So I'll let you know that constant of integration c, those are all just vertical shifts of my function, right? And so think about it. If I draw a curve that looks like that, and I draw a curve that looks like that, both of those curves have the same derivative, right? Because the slope here is the same as the slope here, and the slope there is the same as the slope there, right? They always have the same slopes, right? So they have the same derivative, which means that they're both candidates for being the antiderivative for our function. Okay. So when do we get to write with this integral symbol right here? Right, so we're going to write that the integral of f of x dx equals capital F of x plus c exactly when, well, exactly when this condition right here says that when capital F is the antiderivative, and we get to say that y equals capital F of x is the general antiderivative or indefinite integral of lowercase f of x. So this is the notation that I get to write. When we find an antiderivative, I get to write this sentence right here. There's some pieces to this thing, and I wanted to analyze those pieces, and that's why I put this giant integral into your note sheet. So I think it's helpful. I mean, I certainly find it helpful to digest the individual pieces of it. That right there is just the integral symbol. Right? That's a German S. This thing right here is the integrand. The function that we're integrating, this is the differential. Right? This one tells us what the variable is. Again, that's particularly relevant for those of you who are going to go on to later calculus classes. Regardless of whether you are or not, this symbol has to be here, or else the statement is ill-formed. Or else it's like a sentence without a subject. In a way. It's not a great analogy. This right here is antiderivative. We've got c is my constant of integration. And then the whole thing on the right-hand side right here is the general antiderivative. One thing I want you to note is that, look here, there are no a or b there. That's how you know it's an indefinite integral. No bounds of integration. So let's talk about some basic integration rules. All of these come directly from the differentiation rules. The first one that we have is the zero rule for integrals. This one comes from the statement that dx of any constant k is equal to 0. Or dx of c equals 0. It doesn't matter what you call it. Well, okay, so the integration rules are literally the differentiation rules in reverse. So if I have 0 on the right-hand side, then if I have 0 on the right-hand side, then it's going to go inside the integral, and the thing that was right here is going to go right here. That's literally how that goes. So that means that the integral of 0 is equal to c, because if I differentiate z, I get 0. We don't know what c, some c. I wanted to do the constant rule for integrals too. This one comes from the fact that dx of k times x is equal to k. Hopefully that feels really super familiar. The derivative of a linear function is the slope of the line. And so then I'm going to run it in reverse. I'm going to take the thing right there, and it's going to go inside. I'm going to take that thing, and it's going to go right there, and I'm going to add c. That's literally how I remember these. So the integral of a constant is that constant times x plus c. This is like the integral of 5 dx is equal to 5x plus c. All right, let's turn the page. The power rule for integrals comes directly from the differentiation rule for integrals. The differentiation rule, the power rule for the differentiation rule, the power rule for derivatives. That's what I mean to say. The power rule for derivatives said that dx of x to the n is equal to x to the n minus 1 times n. And I need to kind of do it opposite. So that like, take that and put it here. Okay. No. Take that and put it there. And then take that and put it there. It doesn't really work so well. So how about we go I want blue. dx of x to the n over n is equal to x to the n minus 1. That's true. All I did was move my n over, and then dx of x to the n plus 1 over n plus 1 is equal to n, x to the n. If I just increase all those by 1, of course, this is only valid so long as my n is not equal to negative 1. I think I dropped a negative. Yes, indeed, I dropped a negative sign right there. So the power rule says that if I integrate x to the n, I get x to the n plus 1 over n plus 1. Increase by 1 and divide by what you increased it to, and tack on that constant c. We have to require that n is not equal to negative 1, or else I'd have zeros here, and that would be incorrect. I'd be dividing by 0. The exponential rule is exactly analogous to the rule for differentiation, because dx of e to the x equals e to the x. Fine. That means that the integral of e to the x is e to the x, but because the derivative of every constant is 0, and we're anti-differentiating, I've got to have that constant c. Similarly, if I integrate e to the kx, then I divide by my k, because if I take the derivative of this part right here, I get that part right there. If you want, feel free to pause it and check. And then finally, I don't know why I said the word finally. Next, The integral of 1 over x is natural log of absolute value of x plus c, because the derivative of natural log is 1 over x. This next one here is really important. I spent a little bit of time on the linearity of the definite integral in our last video together. And I wanted to do it again for the indefinite, because it's also true for the indefinite integral. So if I have a sum and I scale, the integral splits across the sum, right? So it splits across the sum. And then I get to pull, my constants out front of their respective integral symbols. So there was an a there and it came out front. There was a b there and it came out front. Right? This plus was inside of the integral, and now I've got two integrals with a plus. We call this linearity. This property is called linearity. One more box of these on our next page, and then we get to do some examples. These are just the trig rules. Literally all of these are just me writing down the differentiation rules for the trig functions. So dx of sine of x equals cosine of x. That's this one right here. Because I differentiate the right-hand side to get the thing inside. I differentiate minus cosine to get sine. Because the derivative of cosine is minus sine, but I don't have a minus sign here, so I need one right there. Right? I need one right there. The other four are the slightly more complicated for the weird trig functions. The derivative of tangent is secant squared. The derivative of cotangent is cosecant squared. The derivative of secant is secant tangent. And the derivative of cosecant is cosecant cotangent. Fine. So I literally remember these in terms of the differentiation forms. So if you made a cheat sheet for differentiation, that's absolutely relevant at this point in time as well. Okay, you ready to do some examples? I am. So let's evaluate the integral of 2 times sine of x minus 3 over x. Okay. The first thing that I'm going to do is I'm going to use linearity. And I'm going to write down that this is equal to 2 times the integral of sine of x minus 3 times the integral of 1 over x dx. Now, you will often see that written as integral of dx over x. So just so you're aware, the integral of dx over x is equal to the integral of 1 over x dx. So now let's attempt to do that antidifferentiation. What do I take the derivative of to get sine minus cosine? What do I take the derivative of to get 1 over x? Natural log of the absolute value of x plus c. It's so easy to forget plus c. Let's do the next one. I chose to do this one because it has tons of power rule in it. But one that's not. It has the weird one. So I'm not going to break this down using linearity. But linearity lets me, I'm not going to explicitly write it down because it's just so much dx. But linearity lets me work on each summand independently. That's so nice. So this is equal to, now I'm going to use the power rule, x to the 4th over 4. Increase by 1, divide by what I increased it to. Plus x cubed over 3, plus x squared over 2, plus x to the 1 over 1. That's this one right here. You can get that either by the power rule or by using the constant rule, plus natural log of the absolute value of x. That's the weird one. Minus x to the minus 1 minus x to the minus 2 over 2. Those ones you might write as like plus x to the minus 1 over minus 1, because I increased the minus 2 right here, right? Because that term right here, this thing is x to the minus 2. So that minus 2 is going to go to minus 1, and then I'm going to divide by it. Okay, let's turn the page. Let's deal with these exponentials. That was one of the exponential rules. Linearity lets me deal with each piece independently. E to the 3t over 3 minus e to the 4t over 4 plus c. Ooh, did I forget my plus c? Oh, I think I forgot my plus c at the bottom here. I did. So easy to do. Simple chain rule in play here for these constants. It works out okay. We're going to learn how to deal with undoing the chain rule when we do u substitution. Undoing the product rule is hard. You'll learn about that in Calc 2. That isn't happening in this class. I really like stuff with parameters, and so, hey, like here's a parameter. It's got a in it. A is a constant. A is just like pi, you know? Like, we just leave pi alone. Let's just leave a alone. Okay. That was just an application of linearity. Let's see here. 9/5 plus 1 equals 14/5. What do I take the derivative to get cosine? Sine? Part of me wants to go back and write this using cursive s's, because cursive s's can't be mistaken for 5s, and this is like hard to tell apart, but hey, sometimes you use s. Deal with it. Let's simplify. I find this unacceptable in its current form. 14 times 5 over 14 s to the 14/5. 14s all cancel. Okay. Huzzah. Are you getting the hang of it? I think it's not that bad. Let's do one with thetas. It initially looks like we might be dead in the water because, like, I haven't told you how to deal with that part. But it's going to be okay. There's a little trick here. Let's see here. Let's take that 6 and pull it out front, shall we? Ooh, I'm missing an integral symbol. There we go. let's write that as the integral of e to the 3 theta times e to the minus 4. That is really ugly 3. All right, do you see what I did there? So this e to the minus 4, that's constant. There's no theta. That's constant. It comes out front. Just gonna hang out. No available simplification. I think this is as simple as it's gonna get. Yep. All right. Not so much left now. I want to talk about differential equations. We do some basic differential equations in this class. We do not do anything where we mix like space and time, or like any autonomous functions. All of our functions are explicit functions of space when we're going to do differential equations in this class. So we're given this thing. That thing right there is the statement of a differential equation, because I've got my differentials and an equation. That is to say that that f right there is given. Maybe I'll put that in red. That's my given. And this thing right here says that that y prime equals f, right? So y prime equals f, find y. So we're gonna give you the rate of change for y, and now we want to undo that differentiation. We want to solve that differential equation and get the original function. What would y have to be such that dy dx equals f of x? And then oftentimes these are going to be paired with an initial condition, a statement like y of x naught equals y naught. That statement right there, that fixes my constant of integration. And when I say fixes, I mean like determines the value of. Because it wasn't broken. So we're given f, we're given a rate of change, and we want to find y equals capital F such that dy dx equals f. We're literally just integrating. That's all we're doing. It's integrating. But this slightly different way of writing this has a tremendous amount of power to it. So even though you might question, like, what is the point of this? The point is all of the incredible power that we get in terms of modeling things like creating turbos, which I think I've mentioned before, because there's this one image that's burned into my mind of this solution of this PDE for this turbo. Myriad modeling problems can be solved by doing this. Fluids keeps coming to mind because I took a couple courses on fluids in graduate school. So while this stuff is going to seem a little basic, it is. And that's because we're training you. So to solve a differential equation, it kind of looks like a two-step process. One, find the general solution. Fine. We'll just antidifferentiate. Okay, and that gets you your y of x. And then the second step, if you're given an initial condition, which you probably are, you're going to plug in your x naught. What are you going to plug it into? To your y of x, the function that you found in step 1, and you're going to set it equal to y naught and solve for c. I think that'll make sense after we do a couple of examples. I have 3 examples planned, and then we'll call it a video, and then come together for our next video when we do the fundamental theorem of calculus part 1. So, first example. Do you like it that I try to get like one thing on the screen at once, or is this just like too much zooming? I don't know. I always appreciate more feedback. So let's solve dy dx equals 4x to the 7, subject to an initial condition that y of 0 equals 4. Let's do that two-step process. One, we're going to antidifferentiate, or find the general solution. No problem. So then y is going to equal the integral of 4x to the 7 dx. And now I'm going to literally do that integral. Y equals 4x to the 8 over 8 plus c. It's important that I have my plus c because in step 2 I'm going to find its value. Okay, so maybe I'll write it in blue here. Y of x equals x to the 8 over 2 plus c. Step 2. I should pan last. Step 2. So what I'm going to do is I'm going to take this 0 right here, that's my x naught, and I'm going to take my 4, that's my y naught, and I'm going to plug those in. So I'm going to have y of x naught equals y naught, generally speaking. Y of 0 equals 4, fine. I'm going to take my 0 and I'm going to put it into that expression. So 0 to the 8 over 2 plus c equals 4. Because that's what y at naught at 0 is. Right? There was an x, now I have the 0. That means that c equals 4. In this case, and for all polynomials, the constant of integration will be equal to that value if that's a 0. Do not generalize too far, because none of those things hold if any of those things are false. Let's do another one. Let's solve dy dx equals sine of t with an initial condition y of 0 equals 2, which will help illustrate my point about plugging things in and not just assuming that the constant is going to be 2. So you might believe that the constant is going to be 2 because in the previous problem, the constant that we found was 4, but it's not going to hold this time. So y equals the integral of sine of t dx. Dt, come on. Did I mess up on the previous one? No, I had x's on the previous one. Okay. Oh, no. Uh-oh. I found another typo. That's supposed to be a t. I have 3 typos to fix before I post this. And I will. What do I take the derivative of to get sine minus cosine? That's what y of t is equal to. I know that y of 0 equals 2. Cosine of 0 is 1, so I have 2 equals minus 1 plus c. Which means that c equals 3. Which means that y of t equals minus cosine of t plus 3. I think I didn't go the distance in the previous problem. I found c, and I think that I need to conclude. I think I need to go y of x equals x to the 8 over 2 plus 4. That was what that's my solution. Then I'm done. Me just stopping there wasn't enough. Keep going, sorry. Yeah, because I want to get to this point right here. No constant of integration left. I have the actual value, the particular value. That's why it's called the particular solution. So labeling things, that right there is the general solution. And this right here is the particular. One more example, and then we're done with this packet. A car traveling with velocity 24 meters per second begins to slow down at time t equals 0. With constant acceleration, a equals a of t equals minus 6 meters per second. Find the velocity at time t and the distance traveled before the car comes to a halt. Okay. So let's kind of piece out what's going on here. I'm given a constant a of t equals minus 6. I happen to know, and I want v of t. And I know that v with a different derivative applied to it, dv dt equals a of t, the derivative of velocity's acceleration. So I know dv dt equals minus 6. And furthermore, I know that the velocity at time 0 is 24. So I also know that v of 0 equals 24. Okay. So these two pieces right here are solve an initial value problem. Okay, so that means that v of t equals the integral of minus 6 dt, where that's my acceleration function. So we'll do that integration, minus 6 times t plus some constant c. And now I'm going to use my initial condition so that v of 0 equals 24 equals minus 6 times 0 plus c, which means that c equals 24. So v of t equals minus 6t plus 24. Groovy. So that was find the velocity at time t. Check. Next, we need the distance traveled before the car comes to a halt. Let's see here. The distance traveled before the car comes to a halt. Let's see here. Well, the distance traveled before the car comes to a halt is going to come from the position function. And I happen to know that ds dt is equal to v of t. The derivative of position is velocity. So that means that s is equal to the integral of v of t dt. That's the integral of minus 6t plus 24 dt, which is equal to, let's use now the power rule. So it's going to be minus 3t squared plus 24t plus some constant c. If you want to be really particular about this, we'll call those c1s and we'll call that c2. That way I'm not reusing the same symbol and as different things in the same context, so because that's a problem. So this is more correct. That's s of t. Now we're going to think about what we want here, because I have the position function, but I don't know this c2. I want the distance traveled before the car comes to a halt. So I need to know, when does the car come to a halt? All right, that's when v of t equals 0, when the velocity is 0. I might write that as v of t sub halt. Well, then 0 equals minus 6 times t sub halt plus 24. I think it's pretty clear that t sub halt equals 4 is the solution to that. The distance traveled, so either I want s of t sub halt, or I want s of t sub halt minus s of 0. And I think they both provide some meaning in terms of this. So they're two different perspectives that I want to share with you. So let's take the perspective that I want s of t sub halt. Well, there's kind of a problem in that I don't know this C2 right here, right? But I think that's okay, because it kind of, like, the value of C2 doesn't matter in a sense that, like, where we think the origin is completely irrelevant. You can put the origin wherever you want, and it's still a distance traveled. So we might as well set C2 equals 0, because we can choose where the origin is. If I do that, then I would have s of t equals minus 3t squared plus 24 times t plus 0. And then s of t halt equals s of 4 equals minus 3 times 16 plus 24 times 4 equals, we'll see here, minus 48 plus 24 times 4 is 48 times 2 is 96. 48 meters. And that's the perspective our book takes when it does this problem. Again, I try to model my my lecture notes pretty tightly after the book so that you can go back and read the book as another resource for these things. But I wanted to also explore this perspective, that what we want is the difference between s of t halt and s of 0. And I think, in my mind, this is the more correct way to do it. In the sense that, like, distance traveled is a delta. Right? It's a distance traveled. Like, how far did you travel if you drove from Eau Claire to Minneapolis? Well, like 90 miles or something like that. And it doesn't matter, like, it's a delta, you know? We're not asking for what the position is at this time necessarily. We're asking for what's the change in position. And so in this perspective, I'm going to leave c sub 2 as c sub 2. T sub halt is still equal to 4. That didn't change. And so what I want is the distance traveled, which is going to be s of 4 minus s of 0. Okay, so s of 4, well, let's refer back to what our function s is. Our function s is up here. That's minus 3 times 4 squared plus 24 times 4 plus c2 minus 3 times 0 plus 24 times 0 plus c2 equals minus, sorry, no, there's not a minus there, sorry, equals 48 plus c2 minus c2. And now what we can see is that the value of c2 didn't matter. Because if you drove 90 miles, you drove 90 miles, and it didn't matter where you started and where you ended, you drove 90 miles. It's the difference between the two positions, and then this constant of integration, the value of it didn't matter at all. We still get 48, right? Those additively cancel, and C2's value is arbitrary. It didn't matter at all. So that is exactly what it means for us to be like, well, we might as well set C2 to be 0 on this left-hand side of here because it didn't matter because it was a delta. And I think this leaves us in a really good position to look ahead to what we're going to do in section 5.4. When we do this definite integration, we're going to be taking the difference of function evaluations to different places. And the constant of integration doesn't matter. It's just going to additively cancel every single time, which is exactly what happened in this case right here. We might as well have set it to be 0 because it's going to additively cancel. So that's what I have to say about the indefinite integral. And when we come back together next time, we'll talk about the fundamental theorem of calculus part 1, which is going to connect definite and indefinite integration. It's going to connect the area under the curve to antiderivatives by evaluating and taking a difference. Exactly as we ended right there. So we just did. You didn't see it, but we just did a definite integral using the fundamental theorem of calculus. We did it. Thank you so much. I really appreciate your time today, and I look forward to talking to you later.